Okay, everyone, today we're going to look at upper and lower boundaries as well as percent error between approximate answers versus exact answers. So these upper and lower boundaries have to do with measurements and kind of a range of potential error humans might make when they take a measurement. And then percent error, what is the actual error between, the exact value of something and the measured value that a human got when they used a tool. For upper and lower boundaries, there are specific ways that we find these upper and lower boundaries. So what we're looking for is we are looking for all the numbers that would round to the given measured value. So for example, let's say our measured value, in that keyword measure, is super important. The problem, if you're on the IB exam or you're on taking a test or doing any practice problems, they will indicate a value is measured. And they're doing that and when they do that, they are indicating that there might be a degree of human error in that measurement. And that error is always whatever numbers round to that value. So let's say my value was 3.5. I'm looking for the range of values that would round to 3.5. And the way we write that range is we always go lower bound, less than or equal to x, or in this case, our x would be 3.5, less than b, okay? And we're going to take a look over here with an example like 7.4. So if I look at 7.4, I want the numbers that would round to 7.4. So I might say, okay, if I start listing some numbers out, 7.39 definitely rounds to 7.4, 7.38, 7.37, all the way to 7.35. Those would all round up to 7.4. I could also round down to 7.4, so I could also do 7.4, 7.43, 7.42, and so on and so forth, okay? But you want to be really careful because a lot of the times I'll have students say, all right, well, my lower bound is 7.35, which is true. You can't really go any lower than 7.35 as your lower boundary. That's for sure the bottom there that'll round up to 7.4. But then I'll have students that'll say, okay, my upper boundary is 7.44, but that's not entirely true because right now that's excluding something like 7.445. That would round down to 7.4 because we would really only focus on this. We wouldn't care about the 5 or any other numbers past it. But if we say our upper boundary is just 7.44, we're excluding numbers that technically would round down. So what we do is we put our upper boundary as 7.45. But this is why we put a strictly less than sign here. Okay? That strictly less than sign is saying, hey, everything underneath 7.45 would round down to 7.4. Okay? But it excludes 7.45 because 7.45 would actually round up, not down. All right? If we come back over to the 3.5 example, my boundaries here in this case would be 3.45. Okay? Though that would round up to 3.5, less than or equal to x less than. And then I would go up to 3.55, knowing that I only put a strictly less than sign there. Okay, so those would be my upper and lower boundaries for the possible measurements. For percent error, we have a formula. So if I'm ever given a true value for something and I have an approximate value for it, I can find the error between them. In this case, what we do, our error is always given as a percent. Okay, that's why it's called percent error. That's why we got the percent symbol there. Okay. V sub A represents the approximate value. V sub E represents the exact value. Okay. And these absolute value bars here are there for a reason. So a lot of the times I'll have students worry about whether or not they need to subtract the exact value from the approximate or vice versa. And it actually doesn't end up mattering, because if you have those absolute value bars, it'll take care of whether or not you get a negative sign. Okay. What really, really matters is that after you subtract the two values, you divide by the exact. Okay. That's what has to happen there. But your answer, because of these absolute value bars, should always be a positive answer. All right. And we're going to do an example in another video after this. So if I wanted to, let's say, find the percent error between, let's say my exact value for the measurement was really 3.53. Okay. So that was my exact. And the measured value, or the approximate value we got, was 3.5. Okay. Notice my exact value fell in that range between 3.45 and 3.55. That should happen every time. Okay. I would plug these into my percent error formula. So I would take approximate minus exact, divide by exact. Okay, absolute values around that, and then I would multiply by 100, and that would get me 0.8498. Okay, and if I wanted to round to three significant figures, 0.850%. Okay, so I would have a very small, in this case, percent error between the exact value and what was measured. All right. I'll do a full example problem in another video that goes through upper and lower boundaries for you all. Okay. It'll be in the same playlist that I have all the other videos here for SL and HL. Again, these are just kind of the general ideas so that you guys can come in and, have an idea of what we'll be doing in the investigations and things. When you come in for class, if you have questions, please feel free to ask. I'm more than happy to help, and thank you for watching.